So far in our study of simple harmonic motion, the equations that we've been looking at apply to any simple harmonic motion situation. We're now going to focus more specifically on a pendulum and a mass-on-spring oscillator. So we'll start off with the pendulum first. The thing to identify here is that we've got a couple of quantities about the pendulum that we need to be concerned about, and in particular we need to be aware of the fact that we have this length of the pendulum that's going to be important, and the angle of displacement here being theta. We've already seen, of course, that its displacement is measured from the equilibrium position. We also know that there's an acceleration that is back towards the equilibrium position. Now, in order to make more sense of this, we actually need to have a look at the forces that are involved, and we can identify fairly easily here that the two forces that are going to be acting on the pendulum are going to be the weight of the mass at the end of the pendulum, so that's given by mg, and then we'll have a tension force that's acting along the string or the wire, whatever it is, of the pendulum itself, given by T. Now, to have a look at that in a bit more detail, I'm just going to draw a slightly bigger diagram over here of those forces that are acting on the pendulum itself. So we've got the weight force acting down, and then the tension force in this direction. Now, the reason why I'm drawing this again is to highlight the fact that we can consider breaking up the weight force into two components. So one component is going to be in the opposite direction to the tension, so that's going to cancel the tension, which means we have another component in this direction that's going to be an unbalanced force. Now, we should be able to identify here, considering the weight force is vertical and the equilibrium position is vertical, and both the tension and this component of weight are along the same line, this angle in here is still going to be theta. So this component that's opposite to the tension will be given by mg cos theta, and the unbalanced component will be mg sin theta. So there's the starting point that we need to be aware of, and we can identify then that the force that we're dealing with that's going to cause this oscillation, F, is going to be equal to mg sin theta, so that component that's unbalanced. So we can calculate what that force is actually going to be, keeping in mind that g is actually a vector quantity. And I should have actually notated that up here as well, apologies for that. So if we look at that particular step, it looks a bit involved with the sin theta term, but we can use what's known as the small angle approximation. Now, for small angles, what it means is that we're dealing with angles that are usually less than about 10 degrees, and we'll deal with this in a little bit more detail in class, but basically what we can identify is with theta in radians, sine theta is basically the same as tan theta, or it's close enough to it. Likewise, that's basically the same as the angle theta itself, and in this situation we can see from the diagram on the left hand side here, sine theta is equal to x on L, so we can identify then that all of those approximations are basically the same, and I'll just note down here where theta is in radians. Now, the reason why this is particularly important might sort of seem that the calculation of sine theta being equal to x on L is a pretty straightforward one. The problem though is that if you look at the acceleration, so this vector here, it's horizontal, whereas our mg sine theta is at an angle to the horizontal. So what we're basically doing with this small angle approximation is identifying that those two can be equated if the angle theta is small enough. So basically what we're going to say then is that if we take this equation f equals mg sine theta, we know that from Newton's second law, the force can also be written as ma, and so that's going to be equal to mg sine theta. And you can see there that the masses cancel, so the mass of the pendulum is not an important factor, so we can ignore that. That then leaves us with a being equal to g sine theta, and using the small angle approximation, so we're going to now treat it as though it's close enough to being horizontal, we can instead write that the acceleration is equal to negative g x over L. Now the reason why we've got the negative in there is we know that the displacement and the acceleration are in opposite directions. So the fact that we've now included the displacement x, that means that we need to include a negative sign there. We're now going to take that one little step further and show that if we take that term of g and combine it with the length L, that's going to leave us with that expression, which hopefully is starting to look a little bit familiar. And instead of writing g on L here, we're going to write omega squared instead. So there's the equation for the acceleration in terms of the displacement that we've already seen. That means then that omega squared is equal to g on L, or taking it a step further, omega would be equal to the square root of g over L. And technically we should have the plus or minus there. Note here that I've dropped the vector notation for the acceleration due to gravity. That's because omega is a scalar quantity. We don't need to worry about the vector nature of the acceleration due to gravity, we only need to worry about its magnitude. So there's omega. We also know that there is another expression for omega, and that's that it's equal to 2 pi on the period t. So rearranging that, we can say that t is equal to 2 pi on omega, and so we can substitute into that and write that it's 2 pi over root g on L. I'm going to drop out the plus or minus here because when we're dealing with a period, we can't have a negative period. Time will only be a positive value, so it's always going to be a positive here. And one last step then, getting rid of this denominator, we can then write that it's that t is equal to 2 pi root L on g. And that's the equation in the data booklet that relates to a pendulum. So you can see from that equation there are only two properties that actually affect the period of the pendulum, those being the length of the pendulum L and the acceleration due to gravity g. So mass doesn't affect a pendulum's oscillation, the amplitude doesn't affect the pendulum's period either. It's only the length and the acceleration due to gravity. Of course that's just for angles that are small, so less than about 10 degrees. If the angle is greater than 10 degrees, then the period might be slightly slower. The analysis of that is far more complex, and so for all intents and purposes, anywhere that we're dealing with the pendulum, we can use this equation to figure out what the period of the pendulum is. Let's now go on to have a look at a mass on spring oscillator, and we'll have a look at that in a similar sort of way. We can skip through a few bits here to make it a little bit quicker, given that we've seen that derivation for the pendulum. So there's a similar sort of approach that we can take here. But before we do, we'll again draw this diagram showing the mass on spring being attached to a fixed object. And if we then extend that, so there's the equilibrium position, if we were to then extend that spring, we would see that there's going to be a displacement that we need to consider. So there's the displacement from there out to there, so that's the value of x. And we would have a force pulling that back in, so the spring having been extended is going to then have a force of extension that's causing it to then be pulled back towards the equilibrium position. That force is given by Hooke's law. Now Hooke's law basically relates to the spring constant, so how many newtons are needed for 1 meter of extension or compression of the spring. So that's the equation that we need to deal with there. It's one that is fairly well known, not one that we'll need to get into in much detail here, so you can sort of just accept that that's the equation that's relevant, or if you need some more detail, let me know and we can talk through that as well. Again though, going back to Newton's second law, we've got the force is equal to mass times acceleration, and we've also got then that force is equal to the negative of the spring constant multiplied by the displacement, where these are all vector quantities. If we take that a step further then, we've got the acceleration is equal to the negative k over m, so we're literally just dividing everything by m here. We end up with that equation. And again, you can see here that we've got the negative, we've got some constant term, and then we've got the displacement with the acceleration on the left-hand side. So again, the acceleration is negative omega squared x. So in this case, omega squared is equal to k over m. So following that same procedure that we did with the pendulum, the period is equal to 2 pi on omega. So in this case, the period is going to be 2 pi over the square root of k on m. And then that leaves us with the equation that t is equal to 2 pi multiplied by the square root of m over k. So there's the equation for a mass on spring oscillator. Note here that it depends on the mass that is moving backwards and forwards and the spring constant of the spring itself. So there's the two equations that we need to know, one for the pendulum and one for a mass on spring oscillator.